Welcome back, everyone. In this video, we're going to start looking at molecular polarity. We've already looked previously at bond polarity and how we can calculate it and determine it based on differences in electronegativity. So now we're going to extend that to molecules. And in order to do this, we need to first talk about what is meant by having a dipole moment or molecule being polar, and then use molecular geometries combined with electronegativity to be able to predict whether a molecule is polar or not. So let's talk about what it means for a molecule to be polar. This occurs when there is a net charge separation between two ends of the molecule. Thus, the molecule will have a negative end and a positive end. In order for the molecule to be polar, or to have a dipole moment, a net dipole moment, then it must meet two criteria. It must have polar bonds, and it must have a geometry where the bond dipoles do not cancel. So, how do we determine whether or not a molecule is polar? In the case of a molecule with just two atoms, then we know it's going to be polar if the bond is polar, because the geometry cannot cancel out. However, if we have more than two atoms, what we need to do is first draw the Lewis structure. Then, we need to determine the molecular geometry of the molecule. So let's say that we're determining the polarity of water. We've drawn its Lewis structure. We've determined that it is an electron domain geometry of tetrahedral, but since it has two domains which are lone pairs, then its molecular geometry is bent. Now we draw in the bond dipoles. Bond dipoles indicate the direction of the partial charge on the molecule. And we draw them with an arrow with a positive side on the tail end of the arrow. In chemistry, the positive side indicates that there's a partial positive, and the arrow points towards the negative side. So we have the electron density coming in towards the oxygen because it's more electronegative. And if we want to determine whether or not these bond dipoles cancel, what we do is we take and we add these bond dipoles together. So what you can see here is that if we draw the resulting bond dipole or the resulting dipole from combining these two bond dipoles, then we end up with a net dipole that points in the direction from the end of the hydrogens to the end of the oxygen. And if we look at the map of electrostatic potential, then we see that there is indeed a difference in charge, that the end of the molecule where the oxygen is has a high negative charge, and the end of the molecule with the hydrogen atoms is more of a negative charge. So what we've done here is we have determined whether or not that the bonds are polar by using differences in electronegativity, and then we've evaluated the cancellation of the bond dipoles. So this brings up a reminder that you need to be able to read maps of electrostatic potential. So as a reminder, when we have a fully nonpolar molecule, then the map of electrostatic potential is going to be green. And the more separation of charge that we get, the wider range of colors that we will get. And so as the molecule becomes more polar, we see the difference in charge take place, where you end up with a deep red color for a negative charge and a deep blue color for a positive charge. And the intermediate colors of green and yellow occur in between. So green is going to be fully nonpolar, whereas yellow is leaning towards the red charge. So I just wanted to remind you that you need to be able to read these types of diagrams and interpret what they mean. So let's practice that. Go ahead and rank the following in terms of increasing bond polarity using these maps of electrostatic potential. Pause the video and try this on your own. Welcome back. So we remember that red means that there's high electron density, blue is low electron density, and green is in the middle. Yellow is moving towards the red color, and so it has a higher electron density than the green. So we would rank these then as molecule number 2 having the smallest bond polarity, whereas molecule 3 is the largest bond polarity. We can see that again because there is no charge separation at all for number 2. Number 1 has a slight separation, and number 3 has a moderate to large separation. Now let's take this one step further. What if you were told that these were 3 different bonds? A beryllium-nitrogen bond, a carbon-nitrogen bond, and a fluorine-fluorine bond. Which of these maps of electrostatic potential would best match the bonds? Pause the video and try this on your own. Welcome back. So we know that since there's no charge separation, then we're looking for something that has a completely covalent bond. That's going to be fluorine and fluorine, despite the fluorine being the most electronegative element. That's because we're looking not for the electronegativity, but the difference in electronegativity. When we look at the position on the periodic table of beryllium, carbon, and nitrogen, we see that nitrogen is farther to the right and therefore has the largest electronegativity of those 3. And so the difference in electronegativity between beryllium and nitrogen is going to be larger than the difference in electronegativity between carbon and nitrogen. All right, let's move on now and reevaluate looking at determining if molecules are polar or not. So let's say that we have carbon tetrafluoride. The first step is to draw the Lewis structure. So we have the Lewis structure here. And for sake of clarity, I have not indicated the lone pairs of electrons on the fluorines, but we know that they're there. Predict the molecular geometry. So we have 4 electron domains. So our electron domain geometry is tetrahedral. And all 4 of those domains are bonding domains. So our molecular geometry is going to be tetrahedral. Now we draw the bond dipoles. We know that fluorine is more electronegative than chlorine, so the arrows point away from the carbon to the fluorine atoms. Then we evaluate whether or not the dipoles will cancel. And this can be somewhat difficult to do. So what helps here is to realize that we have a symmetrical structure. Because the molecule is fully symmetrical, the bond dipoles will cancel out. An easy way to think about this is looking at this image here. We can see that if we look at the resulting vectors of adding 2 of the individual bond dipoles together, that we end up getting a net cancellation across the entire molecule. And so there's no net dipole. If we look at the map of electrostatic potential, indeed, we see that there are regions of high electron density, but there's not one end of the molecule that has them. In fact, it's the center of the molecule. We need to have one end versus the other with a difference in electronegativity. All right, now let's look at ammonia. So let's draw the Lewis structure. This will be nitrogen, 3 single bonds to hydrogen, and 1 set of lone pair electrons. The molecular geometry of this is going to be trigonal pyramidal. Drawing the bond dipoles. So in this case, we know that nitrogen is more electronegative than hydrogen, And so the bond dipoles are going to point from the hydrogen atoms to the nitrogen atom. Now, when we look at whether or not they cancel, this we see is similar to the carbon tetrafluoride. There were 4 domains. However, we don't have the cancellation of that 4th atom. So there ends up being a net dipole that goes from the hydrogen atoms up through the nitrogen atom. And when we look at the map of electrostatic potential, we see that the hydrogen atoms are blue because there's low electron density, and the nitrogen atom is red up on top because of the high electron density. All right, now this is your chance to practice. So which molecule or molecules in that list are polar? Pause the video and try this on your own. Welcome back. So the first steps in all of these cases are to draw the Lewis structures. And again, for simplicity here, I have drawn them without the lone pairs of electrons on the exterior atoms. We see that in all 4 cases, these are tetrahedral shaped. So what's the difference between them? The difference is that they don't all have the same symmetry because of differing numbers of hydrogens and chlorine atoms. For the molecule on the left, we can draw on the bond dipoles, and because we have 4 identical domains, they all cancel each other out, and there's no net dipole. However, for the second molecule, we only have 3 polar bonds. Now, you might be wondering, how do you know? There is a difference in electronegativity. It's not equal to 0, but carbon-hydrogen bonds are never polar. And this is something that you need to know. Carbon-hydrogen bonds are never polar. Thus, whenever you see carbon and hydrogen in a molecule, you can ignore any bond dipole that you might want to put on there. So if we look at the overall molecular dipole of this molecule, we see that it's going down from the hydrogen towards the chlorines. For the second molecule, it could be tempting to draw it out in 2 dimensions and see that you could draw it 2 different ways. One way where you would see that the bond dipoles clearly do not cancel, and another way where it looks like they do. But in reality, this molecule is a 3-dimensional structure with a tetrahedral arrangement. This is a very common mistake. And sadly, some of you will continue to make it despite the warnings that we give. So please pay attention so that way you don't do this. Remember that when we have 4 domains, there must be a tetrahedral arrangement. Therefore, when we draw in the bond dipoles, they cannot cancel each other out completely. There's going to be a net dipole moment. Finally, on the 4th structure, there's only 1 bond dipole, and so we see that it has a net dipole moment. That means then molecules 2, 3, and 4 are polar. So let's summarize here. When you're determining molecular polarity, you need to first draw the Lewis structure, then using VSEPR, determine the electron domain and the molecular geometries. After you've done that, you need to determine whether or not there are polar bonds. You'll notice that there are certain molecular geometries that if the atoms on the exterior are the same, the molecules will be polar always. And these are the geometries that I've shown you here. If we have a linear molecular geometry, if we have a octahedral, a linear from trigonal bipyramidal, square planar, trigonal planar, tetrahedral, or trigonal bipyramidal, if those are the molecular geometries that you have, and if the atoms on the exterior are the same, then we will always get cancellation, even if there are bond dipoles. And that's due to the symmetry of the molecule. Here's one last opportunity for you to practice. So consider that we have a compound containing elements X, Y, and Z. And if the values of electronegativity for each of these are very different from each other, which of the compounds are polar, assuming that all lone pairs are shown? Pause the video and try this on your own, then I will come back and walk you through a solution. Welcome back. So I've drawn for you the Lewis structures, but you need to remember that these molecules have a three-dimensional shape that you need to account for. The answers are listed here for you on the screen. 2 of these molecules are polar and 2 are nonpolar. Now let's delve into why this is the case. Looking at the three-dimensional structure, we can see that the 3 molecules on the left are all tetrahedral. What that means then is that in order to have the bond dipoles cancel out, we need all 4 of these to be atoms, and they need to be the same atoms. Only in the case of the molecule on the left are all 4 exterior atoms the same. Therefore, they cancel out when we look at the bond dipoles. However, the 2 molecules in the middle will not cancel out. That's because if we look at the structure, we can see that there's going to be a difference in pull from the bond dipoles between the elements Y and the element Z. Perhaps Z is not as electronegative, as strongly electronegative than Y is, and so we have a large bond dipole pulling towards the Y. It could go the opposite direction. Either way, as long as they're vastly different from each other, we're going to have a polar molecule. For the third one, we have a case where we have a set of lone pair electrons. That lone pair of electrons does not have its own bond dipole. Therefore, when we look at the bond dipole of the molecule, we see that they will cancel each other out from left to right, but there's a net dipole down. Finally, on this last molecule, because it is a square planar molecular geometry and all 4 of the atoms attached to the central atom are the same, they cancel each other out. That's it for this video. Thanks for watching. Have a great day.